Good afternoon, Henry. Good afternoon, Caleb. How are you guys doing today? Caleb, can you try your microphone and see if it works? Or Henry, doesn't matter. Just want the mic works, and if not, I'm going to jump out and jump back in.
Yeah, can you hear me?
I saw Caleb turn his mic on, but I did not hear anything, so I'm going to jump out real quick and then jump back in, see if we can talk to each other. All right, Caleb, can you try one more time, see if we can hear you?
Can you hear me this time?
I can hear you this time. Awesome. It makes it so much easier when we can talk to each other than having to use the chat box. All right. Any questions from last week's material? Then let's get going on to this. Well, let's do a review of last week's. So in this problem, and I do have my calculator here today, so I'm all set. It says, let R be the shaded region bound by the graph of y is equal to the natural log of x, and the line y is equal to x minus 2 is shown above. Since I moved the diagram, it should be shown below. Find the area of R, okay? So in this problem, all we're doing is we're trying to find the area of this region, okay? So I'm looking at this. I'm gonna have you guys put it into your calculator and see if you can come up with the right answer here. First thing we're gonna have to do, I would assume, is we're gonna have to find this point here, and we're gonna have to find this point here because that is the integral of this thing. So I'm gonna do the same thing. I'm just gonna plug it into my calculator. And I don't know how to use my calculator anymore. Let's see here, natural log of x. And y is equal to x minus 2. And then I'm going to make sure my windows are, I'm going to go from, looks like 0 to maybe 5. And on the y-axis, I'm going to go for, no, I guess I can't go from 0. Y-axis, I'm going to go from like -5 to 5. Let's see if I get a halfway decent graph there. All right, looks pretty good. So now I'm going to go to points of intersection, and I have a really old calculator, so I'm sure my points of intersection takes a little bit longer than yours. I have a 3.14 here. Ha, that's pi. And then down here, let's see here, point of intersection. I gotta move the cursor over. I don't know how your guys' intersection works, but I have to move my cursor to where it crosses that point and then hit enter. And I end up with 0.15. So my integral is going to be from 0.15 to 3.14. I've got the top function minus the bottom function, so I've got natural log of x minus x minus 2. All right. Are you guys on the same page? Is that basically what you guys got? This was 3.14. All right. So what is the area between those two shaded, or what's the area of the shaded region? I'm going to let you guys finish it up. 1.949. Henry, do you agree? And I didn't plug it in to find the area. I just found the points of intersection. So I'm hoping Henry agrees with us. That's 1.949. Use yes. All right. So here is the answer. The intervals, it was 0.1589, 3.14619, and the area was 1.949. Very nice. So finding the area between two curves, very easy to do. And it's not a hard thing to do. In this problem, now this one would be a non-calculator problem. The first one that we worked on, definitely calculator based. This one is a non-calculator based. So let's try this one without a calculator. Now, when they don't give you a calculator, obviously they have to give you values that come out fairly nice, right? Because you're not going to spend all day on one problem. So in this problem, I'm going to do the integral from 0 to 4. And then my top function is square root of x, so I'm just going to write x to the 1/2, minus my bottom function, which looks like x 1/2 x. So there's my integral, top function minus bottom function. Now, you know, being able to set it up is the easy part. Being able to solve, obviously, is a little bit tougher. But if I did this, I'm going to take the integral. So that's what, x to the 3/2 over 3/2, or times 2/3, minus x to the second over, so this is going to be negative 1/4 x to the second, I think, if my integral is correct. And that is going to be on the interval from 0 to 4. Now, this is where, you know, they test so much stuff on the AP test. So now if I put 4 in here, the square root of 4 is 2. 2 to the third power is 8. 2 times 8. So this is going to be 16/3 minus, if I put 4 in here, that's going to be 16 divided by 4, which is just 4. I don't know why I put a line there. Minus, and then I'm going to put 0 in here. Well, that's going to be 0. Okay. So 16/3 more. So that's going to be what, 12/3? So my answer is 4/3. For an answer? Does that look right? So when you think about it, you've got to set the integral up. You've got to take the antiderivative. Then you've got to plug your values in. There's a lot of work to do on these types of problems. 4/3 is the correct answer. Yay! I got one right. Doesn't happen too often. All right. Today we're going to do two things today. We're going to find the volume of solids with known cross sections. And we're also going to find the volume of rotation when there's no middle. We're going to be, I forget what method, I think it's called the disk method. And next week we're going to use the washer method when there's a hole in the volume. So two things that aren't very difficult. Now, when you do solids of cross sections, what they do is they give you a base, and then they tell you what type of figure they're going to put on that base. So in this problem, it says a solid is made so that the base is in the shape of the region between the x-axis and one arc of the curve 2 sine of x. So this is my base. If I draw this line in here, the base is down here. And then they said each cross section cut perpendicular to the x-axis is a semicircle. So here are all my semicircles. And if you put 1,000,000 of these semicircles in here, we're going to add up all of those semicircles to come up with the volume of the solid with the known cross sections. Well, in order to solve this, it's fairly easy. It's the integral from where you start to where you stop. So I go from 0 to pi, and then the area of one semicircle. Now, you can't find the area of one semicircle. What you're going to do is you're going to write an equation of a semicircle and then plug it in here. So semicircle, we know a circle is pi r squared, right? So this is a semicircle, so it's going to be divided by 2. Well, the only thing I don't know in here is my radius. Can either one of you tell me what the radius of one of these circles is going to be? And now you can't tell me a number. You can only tell me like how you would get the radius. So what would the radius be? Okay, go ahead.
Can you put x divided by 2 since it is giving you the diameter?
Ah, very good. But what is the give me the one diameter. Because this equation is 2 sine of x, right? The base is 2 sine of x. So really the diameter is 2 sine of x. If I wanted to know what the diameter is here at 0, I would put 0 in here, right? 2 times the sine of 0, that's 0. If I want to know what the diameter is here at, let's say, pi over 2, which would be this diameter, right? I would put pi over 2 in here. Well, the sine of pi over 2 is 1, so 2 times 1 would give me 2. So I could figure each one of them out. But in general, the diameter is 2 sine of x, so the radius really is 2 sine of x divided by 2, because this would be the radius. So really, the radius is sine of x. That is the radius. So if I wanted to come up with an equation, I'm going to go the integral from 0 to pi of pi times sine of x squared, all divided by 2. That would give me the volume of that cross section, or if you put all those semicircles together. So what you're really doing is you're just trying to find the area of one. Now, you can't find the area of one of them. It's just a generic equation that would come up with them. Okay, let's try a couple more. So in this problem, it said, oh, this one's way too hard. Never mind. We're not doing that one. All right, no. These are, okay. Let's try this one. This one is an AP test question. Now, usually when on the AP test, what they do is they'll ask you to find the area of a piece, and then they'll ask you to find the volume of rotation, and then they'll ask you to find, they'll say the base of a solid. As soon as they say the base of a solid, you're dealing with one of these. So here it says, the region R is the base of the solid. So this is my base right here. For this solid, cross sections perpendicular to the x-axis are rectangles. Okay, so I just draw one rectangle in. Okay, just one rectangle, draw it in there. My drawings aren't the greatest, but there's a rectangle whose height is 10 times its base, and find the volume of the solid. Okay, well, a rectangle, so to find the area of a rectangle, I need to do base times height. Okay, now I'm going to take the integral from 0 to 4. That doesn't look like a 4. And then I'm going to put my formula in here. The formula for one rectangle. All right. What is the formula for that rectangle? Okay. What is the formula for that rectangle? Well, give me the base or give me the height.
The square root of x times 10 times the square root of x.
Oh, very good. You're right. This here is the square root of x. And then they tell me that the height is 10 times the base. Well, that's going to be 10 times the square root of x. So I'm just going to have, square root of x times 10 to the square root of x. Well, square root of x times square root of x is just x. So this is going to be 10x. Now, if I take the integral of that, I have the volume of that base solid. And you have to understand that there's thousands and thousands of these rectangles, but you would find the area of each one of these rectangles the same way. This would be the square root of x times 10 to the square root of x. That would give us the volume of each rectangle. So our task is, all we have to do is find one of them. Once we find one of them, we just take the integral from where we start to where we stop of one of the integrals. Does that make sense? It's a fairly easy thing to do. You just have to, sometimes they get pretty complicated. All right. Let's try another one. Whew, look at that figure. All right, so it says, let R be the region bounded by the graphs of y is equal to the sine of pi x and y is equal to x to the third minus 4x, as shown in the figure above. Now, I can tell you that this is probably part C. Part A was probably find the area of this. Part B was probably to rotate this about the x or y axis. I don't remember, but that's usually how they go. And then part C, it says, the region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. Okay, so I am going to find the area of one square. That's all I have to be able to find on the integral from 0 to 2. Not as easy this time, though. Neither one of you give me what the base is. Well, because it's a square, so it's going to be the same. You know, all the sides are going to be the same. So what is the base, or what is one of the sides of that square equal to?
It's equal to sine of pi x minus x cubed minus 4x.
Oh, so right, because if this is the sine function and this is the y is equal to x to the third minus 4x, it's just top function minus bottom function. That gives us a distance between these two functions. So yes, I'm going to go the sine of pi x minus, and then I'm going to put parentheses, so because that minus sign goes to all those terms, x to the third minus 4x. However, this has to be squared, right? Because this is just the base. Boom. Now if I plug that into my calculator, I should get the volume of that problem. Okay, so I mean, that is one heck of a not a really nice looking formula there, but that is what we would have to do. Now, obviously, that would not be a problem that you would have to do without a calculator. You would definitely have a calculator on that problem. All right. Oh, and here's the problem. The integral from 0 to 2 of sine of pi x minus, and then the answer would have been 9.978. So we did set it up correctly. We just didn't have to solve it. Or we could have if we wanted to. We have calculators, so it's not that hard. All right. So here's a problem that you would get on an ACT test. No, on an AP test that would deal with this type of problem. It says the base of a solid is a region in the first quadrant bounded by the x and y-axis line. X plus 2y is equal to 8, as shown in the figure above. If cross sections of the solid perpendicular to the x-axis are semicircles, what is the volume of the solid? So I'm going to change this to red so it's a little bit easier to see. So I need to find, terrible semicircle there. I need to find that. I'll set the problem up a little bit. I've got the integral from 0 to 8. That's as much as I'm going. Now I want you guys to tell me what the answer is. Okay, I'm going to turn off my mic. I'm going to let you guys work for a little bit. But this is the type of problem that you would see on a multiple choice part of the test of the multiple choice. So I'm going to turn off my mic. I'm going to let you guys work and see what you get. All right? All right, Caleb says the answer is D. All right, now if I was going to do this problem, first thing I'm going to do is I'm going to rewrite this equation because this is a crazy equation. So I'm going to go 2y is equal to negative x plus 8. I'm going to divide through by 2, so y is equal to negative 1/2 x plus 4. Okay, so that's my equation here. If I want to find a semicircle, this is my diameter, isn't it? If I want to find my diameter, I'm going to divide that in half. So I've got negative 1/2 x plus 4. I'm going to divide that by 2, so I'm going to divide each term by 2. So this is going to be negative 1. So the radius is going to be negative 1/4 x plus 2, if I'm not mistaken. That's my radius. Semicircle is pi r squared divided by 2. So this is going to be negative 1/4 x plus 2 quantity squared times pi over 2. Is that the correct formula there? Is that what you had, Caleb? So I'm going to put that up here. So I've got negative 1/4 x plus 2 quantity squared pi over 2. Uh-oh, Henry got C. Oh, that's a huge difference of an answer. 16 to 67. This is what I would have if I set the problem up. Did either of you guys get that equation when you plugged it into your calculator? All right. So I'm going to plug it into my calculator just to make sure. So I'm just going to remember how to do an integral on my calculator. I'm going to go to math, down to integral. Oops. All right. And then I think I have to plug my equation in. So whew, that's going to be one heck of an equation to plug in. So negative 0.25 plus, oops, that's negative 2.5 x. Can't forget the x. Plus 2. Quantity, so that's squared. And then I'm going to divide that by 2 and tack on times 3.14. Comma x, comma, and then I started at 0 and went to 8. I came up with 16.755. How did you get negative 1/4 x? Okay, well, I rewrote the equation so it's y is equal to. Okay, so it was y is equal to negative 1/2 x plus 4. That I just rewrote the original equation that they gave me. Okay, so that's this line right here. Well, so really the diameter, this would equal the diameter, wouldn't it? The diameter would equal negative 1/2 x plus 4, but I want the radius. So what I did is I just divided this whole thing by 2. So I divided this term, so that gave me negative 1/4 x, and then I divided the 4 by 2, which gave me 2. So this, negative 1/4 x plus 2 is the radius. That is the radius. Okay, and then just radius squared times pi divided by 2 would give us a semicircle. Okay, so that should be the correct answer. Nice job, Henry. All right, now today we're also going to talk about volumes, but we're only going to talk about volumes that are solid. Okay, there's really two types of volumes. There's a volume that has a center that's hollow, like if you did a car tire, you've got that middle in there. We're not dealing with that. We're dealing with a solid piece of whatever it is. Okay, so we're going to talk about rotations, but it's going to be a solid rotation. So if I had a shape like this, and I wanted to rotate it around the x-axis, I'm sorry, that would be the y-axis, wouldn't it? That would be the y-axis. I would get something that looked like this, and that's a solid, and that is called a volume of rotation. We're taking a line and we're rotating it around something. Now, let's say I gave you something like this, okay? I gave you the equation y is equal to, let's say y is equal to 2x, and I wanted you to rotate that, okay, I want you to rotate that around the x-axis. What would it look like? Okay, can you imagine what that thing's going to look like if I rotated that thing around the x-axis? A cone, absolutely. And we know how to find, and let's say we're going to go from 0 to 4. We know how to find the volume of a cone, don't we? Volume of a cone is it's base, now I have to think about it because it's a radius. Okay, so area of the base times height. So area of the base is going to be pi r squared times height. Okay, so volume of this thing is going to be pi r squared h divided by 3. Okay. Oh, somebody forgot a pi in there, Henry. Because if it's a cone, the bottom of that is going to be a circle, isn't it? So volume is always area of the base times height, and if it's a cone or a pyramid, we divide by 3. So in this problem, it's pi r squared times height divided by 3. So in this problem, what is the height? So my cone is sitting sideways. I'm going to turn it upright. Okay, so I kind of a bad cone here. Right. So what is the height for this cone? 4. I agree. The height is 4. So I've got height is equal to 4. What is the radius? What is the radius of this problem? 8 is correct. So now I have all the information to find the volume of this cone. So I just take my volume is equal to pi times r squared. Well, r is 8, so that's 64 times height, which is 4, divide by 3. I don't know why my 4s keep looking like 9s. All right, so if I multiply that out, I've got 64 times 4 times 3.14 divided by 3. I come up with 267.94. Let's say this was inches. So I've got inches cubed. Okay. So that is finding it geometrically, right? So now let's talk about finding the volume using an integral. Now I wish I could erase. Okay, we can remember that the answer was 267.95 because Henry put it in the chat box. Okay, so I'm going to erase this, get rid of that. So now we're going to do the same problem. We're going to use calculus on it. Okay, so again, we had this was y is equal to 2x. This was from 0 to 4. So now if I wanted to find an area of rotation, all you do is you draw in, since this was the x-axis, you just draw in a radius. This is my radius. What is the radius of this thing? So I'm going to rotate this around the x-axis. The radius is 2x. Okay. So if I want to find the integral, I just go from where I start to where I stop, so 0 to 4, and then radius pi. I have to put a pi on front. Sorry about that. Integral of radius squared. That's it. And if I did that, okay, so my radius is 2x. So if I do this, radius squared, so that's 2x squared. So that's really 4x squared, isn't it? So I've got pi times the integral from 0 to 4 of, what did I say, 4x squared? So now if I take the integral of this, I get 4x to the third over 3 on the interval from 0 to 4. So if I plug 4 in here, I'm getting my calculator out because I don't want to do this by hand. So I've got 4 raised really to the 4th power, don't I? So that's 256 over 3. If I put 0 in there, I just get 0. But then I have to multiply by pi at the end because I have pi on the outside. So 256 divided by 3 times 3.14. And my answer is 267.95. Ho-ho! Get the exact same answer using calculus that I did using geometry. So finding the volume using an integral, it's just one radius. So all we'd have to do is find one radius. So we just take radius squared, the integral from where we start to where we stop, of 1 radius squared times pi. That's it. That is all we're doing. All right. Got a bunch of, this is called the disk method because there's no holes in it. Next week, we're going to be talking about the washer method because we're going to have a hole in the middle, and so we have to subtract off. Now, when you have the washer method, it's just big radius squared minus small radius squared, right? It's just big minus small because you're going to find the volume of the whole thing, and then you're going to subtract off the whole, and that gives you the volume. But this week, we're only going to deal with the disk method. Here's our formula. Volume is equal to pi times integral from a to b of radius squared. That's it. Right, so let's try a couple examples. All right, now, too much space taken. Oh, I think we've seen this problem before, but now we're dealing with the volume of the solid generated by revolving r about the x-axis. Now this, again, would be a problem that you could not use your calculator. You can tell when you can use calculators and you can't, usually. I mean, they give you values that you can absolutely take easily. So can somebody set this problem up for me? How would I find the volume of rotation for this one?
So the square root of x is your radius. So you do pi times the integral from 0 to 4 of the square root of x squared. So of just x.
Yep, absolutely. And now you can see why this should not be a calculator problem, because you should be able to do this. This is pi times integral from 0 to 4 of x. The integral of x is just x to the second over 2 from 0 to 4. If I put 4 in there, 4 squared is 16. 16 divided by 2 is 8, so 8 pi should be my answer. All right, somebody came up with 12.56. I don't think 8 times pi is 12.56. Did I do something wrong?
Nope, I forgot to integrate.
Okay. I was going to say, there's no way 8 times pi is 12.56. Okay, so this should be my answer here. All right, so finding the volume of rotation, fairly easy thing. All right, so this problem here, I think it's got a bunch of different things. Find the area of R. Find the volume of solid of rotation when R is rotated about the vertical line x equals -1. I hope that's not a, hope that doesn't create a hole. This might create a hole. Let me I better graph this out and see if that's going to create a hole, because it might. X, the square root of x, and we're not talking about those types of problems yet today. So that's the square root of x. X, 1/3 x, so that's going to look something like this, I would assume. I'm assuming that this is, definitely is going to be, this is definitely going to be a volume of rotation with a hole in it, because x equals -1 is over here. And if we rotate that around there, there is definitely a hole in this thing. So that is not a type of problem that you should get tonight, because everything that we're doing tonight is a volume of rotation that doesn't have a hole. Now, obviously, you guys had this class last year. You probably can do the problem, but you shouldn't have anything like that tonight. The disk method is still just pi. It's pi times the integral from where you start to where you finish. It's still pi, but then it's big R squared minus small r squared. That's it. The washer method is just big R squared minus small r squared. But we're going to just spend all next week on that. So this should not be a problem on this slide. That should be a problem on next week's slide. Yeah, no, bad. All right, so let's try this one. If the region enclosed by the y-axis, the line y is equal to, and the curve y is equal to square root of x is revolved about the y-axis, the volume of the solid generated is, okay, so now we're revolving around the y-axis. Makes it a little bit more difficult, I will say that. Okay, so here, if I did this problem, y is equal to 2, so that's just going to be a horizontal line. Okay, so this is y is equal to 2. And y is equal to the square root of x. Oh, that's a pretty bad graph of that. All right, so that square root of x, that's really a bad. Oh, I can't even look at that. It's too bad. All right, so I'm going to try this again. Let's see here. Let's get a color here for my line. All right. So let's see if I can draw this a little bit better this time. So y is equal to 2. Should be a horizontal line. All right. And then I've got y is equal to the square root of x. So that's going to look like something like this. And they're going to meet at, what, 4, 0, if I'm not mistaken? So I'm taking this function, and I'm revolving it around the y-axis, okay? So when I do that, instead of, my integral is going to go from start to finish. So my integral is going to be from 0 to 2. Now, The trick on these is you have to rewrite each equation as x equals. So instead of having y is equal to the square root of x, I have to rewrite this as y squared is equal to x. That's the equation I want to use. Okay? It has to be x equals. So now this is my radius here. And what is the distance from here to here? It's just y squared. So my radius in this problem is y squared. So remember, so now we just go y squared squared. And I'm going from 0 to 2. So if I rewrote this, this would be y to the 4th. So I've got pi integral from 0 to 2 of y to the 4th. So if I take the integral here, it's y to the 5th over 5, an interval from 0 to 2. If I put 2 in there, 2, 4, 8, 16, 32, so that's going to be 32 over 5 pi. Woo-woo! I love it when my answer comes out right. But the key to when you revolve it around the y-axis is you have to rewrite it in every equation as x equals. All right, that is the key to those types of problems. Is you just have to rewrite it as x equals. Okay. Any questions on those or on that one? No, the shell method is, you don't ever have to know the shell method as long as you know the disk method and the washer method. The shell method never comes in, never. Everything, every volume can be solved using the disk method or the washer method. There isn't a problem that they can give you that you have to use the shell method for. The washer method really takes care of that. So no, never have to use the shell method. All right, this is the last problem I have for today. I'd like you guys to work it out and see what you get for an answer. I'm going to turn off my mic so you guys can work without me yapping away. Uh-oh, I'm looking at this and I'm thinking this, well, maybe it's not. No, I think, okay, I think this is a disk method problem. So, any answers? No. This seems like I'm thinking y is equal to 2, and it's x equals 2, which is a vertical line. Yeah, this looks like a washer method now that I look at it. So if you have, yeah, definitely washer method. So if you have this, and we have y is equal to x squared, which would be this graph here, and x equals 2, which would be this graph here. That is definitely going to be a washer method. So they've got this. You keep getting 6 pi? Yeah. Is this the diagram that you had? Okay. So let's just try it. Revolve around the y-axis. Okay. So the first thing I do anytime I have y-axis is I'm going to rewrite this as x equals. So this is going to be x equals the square root of y. All right? So that is what I'm going to use here. X equals 2, I can't change that one. So that's going to be x equals 2. And where do they meet? They meet at 4. Well, yeah, they meet up here at 2, 4. So if I'm going the y-axis, it's going to be from 0 to 4, right? Because I have to use the y-axis as my interval. So I've got the integral from 0 to 4, big radius minus small radius. So my big radius, that's my big radius. So that's just 2 squared, isn't it? Minus my small radius. Well, my small radius, that's just the square root of y, isn't it? But that's also squared, isn't it? Because it's big radius minus small radius. So if I was going to do this problem, I'd end up with, I have to put a pi on the outside. So that's going to be 4 minus y. That seems fairly easy to come up with an integral. So that's going to be 4y minus y squared over 2 on the interval from 0 to 4. So if I put 4 in here, I get 16 minus 16 over 2, which is 8. And then if I put 0 in here, I end up with just 0, right? So I end up with 8 pi for my answer. Right, because remember, you have to take the integral has to, if we're rotating around the y-axis, this is going to be our interval. So our interval is going to go from 0 to 4. And that is a preview of next week. I didn't do it on purpose, but that's basically what we're going to do next week. Next week, we're going to be dealing with volumes of rotations when we have to use the washer method. All right, any questions on any of the stuff that we went over today? You guys have a great week. Make sure you stay inside on Thursday and Friday. It's supposed to get really cold. But then if you take a look at next week, it's supposed to be in the 40s. Woo woo! Spring is here. I can feel it. All right, you guys have a good one. Bye.